And we are rolling. All right, guys, welcome to the second half of FM 5032. My name is Preetham Dalal. You can just call me Preetham. I was part of the first class in the MFM program, which is becoming a less and less cool statistic as every year passes by. But I was not part of the inaugural graduating class because I did take a few years to graduate. And I think you could do the program in 1 year back then. So there were some go-getters who got done in 1 year. So yeah, I've had a variety of sort of trading and analysis roles, mostly here in the Twin Cities. And I'm actually starting a new endeavor at the end of this month with our studio in sort of a sales engineering type role where I'll be working in the finance and insurance vertical and helping them sell their enterprise level products. So I'm super excited about that. And I hope I didn't just jinx the whole thing by announcing before I've actually started. So, but anyway, so that's a little bit about me. So yeah, so I've titled my module Data Analysis and Machine Learning in Finance. So really the first probably couple tutorials, early tutorials are gonna be more on the data analysis side, which I consider to be anything working with data frames and trying to do analytics on them. But that's not, you know, straight up statistics or predictive modeling, which I consider both of those to be more the purview of machine learning, which is going to occupy most of this course. So most of this class is going to be working through these tutorials. And if any of you guys have taken a class from me, you kind of know the drill by now. There are these interactive tutorials where I encourage you to type along as best you can, just to work that muscle memory and get used to writing the code. And I think it'll help you understand that better. I will say in this class, some of the code chunks get so burly that that's not really feasible, but I try to adhere to that as best as I can. But I do a lot of uncommenting and running myself as well. All right, cool. So, okay, so in most cases, there are going to be two versions. There's going to be the filled version, which basically has everything which basically has just the code and it's all run and everything like that. And there's this other one that has all the code, the not filled version, has all the code commented out, and I like to type live code it along with you guys, or for you guys. Now, like I said, there's just, in more introductory courses, this works a lot better. I still think it's a good practice, but you know, there's crazy stuff down here that we're not going to type out. So cool. So let's go ahead and get started. So as you guys are probably very familiar with by now, the Black-Scholes-Mertion model is one of the foundations of quantitative finance. So not only does it provide a theoretical pricing framework for options, but it also gives a practical engineering result. And really what it gives is a manufacturing process for derivatives desks to employ to construct options that their customers want to trade. And it's this manufacturing process that gave birth to really the entire derivatives industry. And Zora is an expert at this stuff, working at Cargill Risk Management. So she knows all about this at a day-to-day level. So the purpose of this notebook is to explore this option manufacturing process that's spelled out in the Black-Scholes-Mertion result by performing data analysis on some simulated data. So you guys have probably seen, you know, like mathematical formulations of this with DWs and stuff like that. But this is going to be sort of a data analyst's approach to trying to understand that same issue. But we are going to use some, you know, the stochastic process, geometric Brownian motion stochastic process, and generate paths from that. And so this will be, yeah. So, okay. So we begin everything by always importing the packages that we need. So we're going to import NumPy as NP, import Pandas as PD, and PD options display. Oh, it can't autocomplete yet. Max rows equals 10. All right, cool. And so this last line was just to make things prettier, I want to just display 10 rows every time I print a data frame. Oh yeah, and let me actually do this. I'm gonna actually increase the size here. Hopefully that makes it a little bit, ooh, got a little overzealous. Okay, so, another thing that that you guys, so this tutorial requires a package called pyvollib. It's definitely on pip. I don't know if it's on Conda or not, and I don't know how you guys have it installed. So, but what I do is I just do, I have to say pip3 install pyvol, what is it? Is it py_vollib? Yeah. I don't think I'm doing anything for me. So I'll give you guys a second to just download that or install it. All right, so I'm not actually going to type any of this out. Oh, and I don't know if you guys you've probably learned this trick already, but if you hold down Alt, you can highlight blocks of code like this. So we're going to import a variety of functions from the pyvollib package. Black-Scholes-Mertion, which is just the standard pricing formula. Then a couple for the Greeks, delta and Vega. And then finally, the implied volatility function, which we will use. So, all right, I'm going to break my rule a lot of like typing during during this tutorial, just because there's just so much code and I don't want to mess with it. So, okay, so pyvollib, these functions actually look like this, right? They take, a call, like is it a call or put, individual inputs. But we want to basically vectorize our code and be able to use the dataframe.apply method. And so we need to convert these functions such that they can accept a row of a data frame as an argument. So that's what we're going to do here. So all this code is saying is, all right, I'm assuming that that the input is going to be a row of a data frame and that all these columns will be present in the row. And then I'm going to pull out all of the inputs, call put, underlying price, strike, et cetera. And then I'm going to actually calculate the Black-Scholes, the price from it. And I'm going to round it to 2 just to keep things nice looking. I'm also assuming a risk-free rate of 0 and a dividend yield of 0, just to keep things simple, since this is simulated data anyway. So those are hard-coded in here. And then we do the same thing for delta and for Vega. Okay, so let's run those code chunks. All right, any questions thus far? Okay, so let's talk a little bit about geometric Brownian motion, which you guys are probably familiar with. So, the series of trade prices for a stock is often modeled by a series of random variables, which we typically call a stochastic process. So there are lots of different types of stochastic processes. Some of them resemble stock price movements better than others. So, so the Black-Scholes-Mertion option pricing framework assumes that the price process of the underlying asset follows a geometric Brownian motion. So what exactly does that mean? It means 3 things. 1, the price process is continuous. 2, the log return over any period of time is normally distributed. And 3, that the returns during any 2 disjoint periods of time are independent. And so, as it turns out, none of these is actually true or even close to true. But well, close enough to true for this to be a reasonable framework and for the manufacturing process that it prescribes to actually be useful in the real world. So, yeah, and it's geometric Brownian motions are one of the simplest types of processes that reasonably model asset price dynamics. So the price process of a geometric Brownian motion is determined by the current risk-free rate and the annualized volatility of the underlying, especially in this, and dividend yield is in there, but we're assuming it's 0, so I didn't even include that. So for prices that are separated by delta t units of time, they're related by the following equation. So if the current price is st minus delta t, then you multiply it by this exponential expression. And in here, this zt is a standard normal random variable. And so that's what makes it random. And that gives you the price in the next step, in the next time period. So, and one thing to note here is that this expression here is the log return of the asset over this time period. So this is called the Euler discretization for the geometric Brownian motion, and it's going to be the recipe that we use for generating price paths in our simulations. Okay, so like I mentioned above, geometric Brownian motion is certainly not reflective of reality, but it's close enough that derivative dealers can construct contracts for their customers in using the manufacturing process that's described in the Black-Scholes-Mertion framework. So this is often referred to as constructing a replicating portfolio. And in the case of vanilla options, this replicating portfolio is a dynamic trading strategy involving the underlying asset. So it means you basically hold different amounts of the underlying asset at different periods of time, and sometimes you hold more than others, and that's why it's dynamic. So you have to buy and sell, and this is referred to as delta hedging. All right, so this is just a little throwback discussion questions. So throughout my tutorials, I like to throw out discussion questions and little code challenges just to make sure I haven't lost my internet connection and you guys can still hear me. And just keep you guys on your toes. So if you recall, put call parity is a pricing identity that emanates from a static manufacturing or replicating strategy. So I just want to make the distinction between there's delta hedging, which is dynamic, but there's also static hedging strategies or static manufacturing strategies. And put call parity emanates from one of those. So see if you can recall what kind of, I guess what the nature of that replicating strategy is. So what are the put and the call, like what combination of those are you holding, and what other type of derivative are you constructing from a put and a call? So I'll give you guys a few minutes to noodle at that. So put call parity comes from the observation that if you have a put and a call, both at the same strike, same time to expiration, and you have a long position in the call and a short position in the put, you end up with a perfectly linear payoff, i.e. a forward contract to buy. So yeah, if you're long call and short of put, that's a forward contract to buy at time t or whatever time in the future at the strike price k or the forward price k. And so that leads to the following identity. CKT, if that's the price of the call, minus the price of the put, equals, and so this is just an identity from derivative pricing theory, something like this. Maybe put present value of the forward price or the strike price. So that's put call parity for you. But I guess the real point I want to make, well, I wanted just to refresh around this because it's a super important identity in option pricing theory, but also because this is a static hedging strategy. If you take a long call and a short put, you just hold that position to maturity and you have a forward contract. Delta hedging, an option position, is different because you are dynamically trading the underlying. Hold on. All right, so we are going to perform some analysis on one particular option and what it looks like to hold that option position and delta hedge it, and what kind of P&Ls that results in. So I actually grabbed data for one particular option that was trading in the market, and so the underlying was QQQ, and that is the ETF that is an ETF that tracks the NASDAQ 100 index. The day that I grabbed this option price was November 16th, 2018. The expiration was December 21st, 2018, so a little over a month later. It was a put with a strike of 160. It was out of the money because the underlying price was at 168 above the put strike, and it had 24 business days to expiration, and the price of the option was 225. So from all this information, we can actually calculate an implied volatility, and later, for reasons that'll be clear, we'll refer to this as the pricing volatility. So, and I will note that this is the typical flow of events, that for the most part, most market participants are just observing option prices and from that calculating implied volatilities. Although oftentimes, I don't know, in the way it's presented in courses, it makes it seem like you have some implied volatility in mind, you stick that into Black-Scholes and you get a price out. The truth is the prices are what is moving, and people talk in prices and then translate it into implied volatilities in certain contexts. Okay, so let's go ahead and calculate the implied volatility. So I'm going to say pricing vol equals implied. Didn't I run this up here? Oh, I didn't even run this. My goodness. I don't think it matters actually, but implied volatility. The price was 225. The underlying was at 168. The strike price of the option was 160. The time to maturity is 24 divided by 252 because there are 252 trading days in a year. The risk-free rate is 0. The dividend yield is 0. And the flag is equal to P because this is a put. See if that runs. Okay, cool. And I'm going to actually round this to 0. Cool. So that's our pricing vol. This is the volatility we're going to use when we generate our simulated paths. Let's talk a little bit about, let's simulate a single underlying price path and delta hedge along that path and see what exactly that means. So typically what happens is a derivatives dealer will trade the above option with a customer and then hold that option position, that's a typo, that option position until expiration, and then delta hedge it on a daily basis. So the Black-Scholes manufacturing framework states that the dealer will break even, is going to break even by doing this. if one, the underlying price process follows a geometric Brownian motion. Two, the realized volatility during the life of the option is equal to the implied volatility. And the dealer delta hedges with frequent rebalancing. So this is actually a probabilistic statement. So this is really the dealer will break even on average if the delta hedging is frequent but still discrete. And the more frequent it is, the more deterministic this result is. But in order to be purely deterministic, as is stated by the Black-Scholes framework, you need to delta hedge continuously, which is just a theoretical fiction. So part of what we're doing here is you're going to see that when you're discretely delta hedging, even in the very plain vanilla Black-Scholes-Mertion setup, there is still a huge amount of variability in discretely delta hedging, and it's not deterministic. So but we'll see that in a little bit. Okay, so what we're going to do is we're going to generate a single price path starting at 168, and then we're going to see what it looks like to delta hedge on a daily basis along if the underlying price took that path. So let's go ahead and just look at this. I'll let you guys noodle around with this code. But I guess the main thing I'll say here is that this is the real, I don't know if this was a joke or not, memorize this line, but this is the Euler discretization from up here. So that's it in code format, and so basically what this is doing is looping through the days and just generating paths. So let's go ahead, generating a path, one given path. So let's take a look at what this looks like. And it stuck everything into this array called single paths. I think it's an array. Yeah, it's an array. Cool. So as you can see, we start at 168. It jumps all the way up to 172.57, then back down to 170.80, and it ends up at 164.10. So the put in this situation does end up out of the money because it was a 160 put. Okay, so the next thing we're going to do here is we're going to create a data frame that's going to basically hold all of the data that we're going to need in order to price and delta hedge this thing and see what the P&L looks like and track that P&L. So I'll just run this code. And as you can see here, where the underlying is QQQ, it's a put 160. The pricing volatility is 26.36, 26%. Here's the price path. This is where we put in the price path, 168 all the way down to 164.10. Days to maturity ranges from 24 all the way down to 0. I put this buy sell here because we're going to reuse our code to do buys and sells. And so just to get it all in one place. And the time to maturity is just the days to maturity divided by 252. All right, let me stop a moment and see if there are any questions so far. Oh, okay. Nice. All right, let's forge ahead. So basically we're going to add columns to this data frame that's going to help us track the P&L. So the first thing we're going to do is we're going to add the option price as a column to this data frame, because as the time to maturity decreases and the underlying price changes, both of those are going to affect the option price. And the nice thing about writing vectorized code is you can do this all with a small amount of typing. So we'll say DF path option price. We're going to add a new column called option price equals to DF path CP UPX strike T2X Yes, is there a question? You got my hopes up. I thought we were going to talk. Okay, cool. So I'm using this apply function. I don't know if you guys have used it in your other class, but it's cool. It basically vectorizes code. And for those of you who have taken my Python class, you probably remember that. Okay, cool. So so now we have the option price, how the option price is changing through time. Of course, it starts at 225, which is what we observed in the market, and we calculated the implied volatility based off of that. But holding that volatility static, all that's changing is the time to maturity is changing and the underlying price is changing. So when the underlying price goes up, the put is worth less, so the option price is going to go down, et cetera, et cetera. And then finally, on the last day, the option is out of the money, and so it's going to be worthless. Cool. So next, we're going to add delta as a column because we want to be delta hedging. So we need to calculate the deltas, which is going to indicate to us what stock position we should hold. So DF path delta equals DF path CP UPX strike T2X volatility, and then apply BSM delta axis equals to 1 DF path. Cool. So now we have the deltas. This looks right because a put has negative delta. Starts at about a 26, ends up at 0, obviously, because it's an out of the money option. So here's a pop quiz question for you. If the option ended up in the money, what would the delta have ended up as? Any brave souls? You can put it in the chat. It would actually end up as -1 because when an option's in the money, right at the moment of expiration, the payoff is going to track 1 for 1 with the changes in the underlying. Okay, great. So now let's calculate the option P&L, which for us is just the difference between this option price and this option. Well, no, we're long the option, so it's the difference between yesterday's price and today's price. So DF path option P&L equals DF path buy sell times DF path option price DF path. Okay, cool. So as we can see, yeah, we were long the option. It went down in value quite a bit because the underlying price jumped up quite a bit. So we lost $1.04. We gained back 23, another 23, et cetera, et cetera. Okay, great. So that's the option P&L. And delta hedging with a daily rebalance means that at the end of each day, we're going to hold a position in the underlying whose size is equal to the negative of the delta of the option position. So the daily delta hedging P&L is calculated as follows. Oh, so just to be clear here. So basically at the end of this day, we're going to hold 0.261 units of the delta of the underlying. At the end of day one, we're going to hold positive 161 units of the delta. So to go from this position to this position, since it's the negative, we're actually going to need to sell about 0.1 units of delta. So that's how that works. So let's calculate the DF, the delta hedge P&L, as follows. DF path, delta hedge P&L equals negative DF path by sell. So this little bit of code is what allows us to, because you do everything in the reverse if you're short. So yeah, delta shift 1. And the shift 1 is because the P&L for today is based off of the delta held at the end of yesterday. All right, guys, so here's a discussion question, just to see if you're following me here. So what was the delta hedging position held at the end of day, not at the end of D2X, at the end of day 21? Well, no, actually, that's fine. I don't actually remember how let's interpret this as the end of day 21 right here. And so yeah, what was the delta hedging position at the end of that day, and what was the trade that was executed at that time?
So since the delta decreased from 0.472 to 0.714, does that mean that we're selling 0.242 of the underlying? You have
the exact right idea, but you hold the negative of the delta. So so the delta, I say the delta increased because I think in terms of absolute delta. So so I think you had it right, but so you're going to hold at the end of day 20, you were holding positive 0.472, and so you need to buy whatever the difference is between 0.714. We just calculated it out. So 0.714 minus,
I think it's 0.242.
0.242. I suppose I could actually do it in Python. Okay, so does that make sense? You would actually buy, so you end up with 0.71 units of the delta, a long position in 0.714 units of the delta. And in order to get there, you need to buy 0.242 because you started you ended the previous day with a long position of 0.472. So that's the sense in which this is a dynamic strategy, is that you're constantly rebalancing your delta and buying and selling based on what the current delta of the option is.
Is that okay if I add something here?
Yeah, Zora, go ahead, please.
Nice. So we're long put. As you see, the delta is negative. It should be always between 0 and -1 because we're long put, but your gamma is positive. Gamma being positive means that you always make money with your delta hedge. So if you see the price goes down in 21 from 160 something to 157, the price goes down, but you're buying future to do the delta, but you're buying for cheaper price. And when the price goes up, then you have to sell, and you're selling for higher price. That's how you make money with your gamma here. Thank you.
Yeah, thanks for that, Zora. So, all right, so let's calculate the total P&L, which is just your option P&L plus your delta hedge P&L. DF path total P&L equals DF path plus DF. Cool. All right, so that's the total P&L, which is just your option P&L plus your delta hedge P&L. And you can see that most days is pretty close to zero, not perfectly, but that's what you'd expect, right? Something like that. And if the more frequently you rebalance, the smaller in magnitude these numbers are going to get. So if we want to look at the cumulative P&L of this entire delta hedged option position, we'd say DF path total P&L is 18 cents. So that's pretty close to zero, but it's not exactly zero. And the option price was 225, so 18 cents divided by 225. You know, that's 8% of the option value, which is not a ton, but we'll see that we kind of got lucky in this situation and things can deviate quite a bit. So, okay, so here's a little code challenge. It's copy and paste the code above into this space below here, and then modify it to calculate the P&L for selling this option for 225, and then delta hedging it over this same scenario. Yes, Brady, you're exactly right. So so Brady said, is it about -20? So so just one kind of rule of thumb is that if you have a long derivatives position and it has a certain P&L, if you took a short position, the exact same position but a short version of it, or the short side of that position, then you should have the negative of that P&L. So buying an option and delta hedging it is the exact opposite of selling an option and delta hedging it. So I copied and pasted all this code above, but there's this buy sell column, which basically controls whether you're going long or short. And so as you can see, it's exactly negative that. So that's just kind of, the intuition is what I described, that if the P&L from a short position is the negative of a P&L from a long position. But this is a way that really we actually calculated out from first principles and saw that to be exactly the case. Okay, any questions on that? And thanks again, Brady, for stepping up. Okay. All right, so as we saw above, our P&L was positive 18 cents, pretty close to zero, but this was just for a single path, and we might have just gotten lucky. And the truth is we did get lucky. And as we'll see below, you know, if we generate a variety of paths and then analyze the results of the distribution of the resulting P&Ls from delta hedging over all those paths, we'll see that we can significantly differ from zero sometimes. Okay, so I'm gonna go ahead and so this is basically, these are all the sort of preliminary values for our scenario generation. It looks like I'm actually gonna sell an option rather than buy. It doesn't really matter. Again, it's just the negative. 24 days to expiration. These are all the option price things. Pricing vol is the implied volatility. Path vol is a pricing vol. Okay, so the hedge frequency, so we're gonna hedge 24 different times, so basically once a day. So the the amount of time between hedging is the full tenor of the option divided by 24. So basically one business day. Risk-free rate is going to be 0, and we're going to generate 1,000 paths. So let's go ahead and initialize an array. This is going to hold all our paths. And I believe the paths are going to go down column-wise. I always forget. So let's set the initial price for all our paths to be the spot price of 168. Cool, yeah, so each column of this array is a path. So, right, so if we use the broadcasting capabilities of NumPy arrays, we can write our scenario generation in just a few lines of code. So this is actually less lines of code than it was for generating a single path. Cool. So here we go. We've got 1,000 different paths. They all start at 168. This one ends up at 164.14, et cetera, et cetera. Okay, so what I'm going to do here is, this is basically a succinct version of the same code that we had before, but we're just going to grab one path. So we had multiple paths. We're just going to grab one of them, and then this generates the same data frame that we generated before, but all the code is in one place. And let's just calculate the resulting P&L. Actually, make this a little bit bigger. No, kind of need to be able to see stuff. Cool. So for this particular path, we end up at losing 161, and that's a significant portion of our option price. So as you can see, sometimes this you can deviate quite a bit from 0. All right, so this big chunk of code basically just repeats this this process of calculating cumulative P&Ls for all the scenarios. Not just cumulative P&Ls, but like delta hedge P&Ls, total P&Ls, all that stuff. So you'll see. So we'll run that, and we'll see what the resulting data frame looks like. Cool. So as you can see, we've got 1,000 scenarios. The first one is scenario 0. The last one is 99. And then we have the same set of columns before. We have the option P&L for that scenario, the delta hedge P&L, and the total P&L for all those scenarios. So let's actually use a group by statement to calculate what the total P&L is, the cumulative total P&L is for each scenario. So we're going to say df P&L equals df all paths, which is this data frame up here, group by scenario as index equals false, total PNL, DF PNL. Okay, so here are the total PNLs for each scenario, and here's, you know, the negative 161 that we saw from above. Okay, so let's see what our average PNL is. By just taking the mean of all these. Cool. So there you can see the average PNL of delta hedging, doing a delta hedging exercise over all these scenarios is very, very close to zero. But any individual path can deviate from zero significantly, as we've seen. And you can see here, negative 162, positive 171, 175, et cetera, et cetera. So here's a discussion question for you. If you sold this option for 25 cents more than fair value, what would the average P&L be here? All right, guys. So we'll just kind of talk through some of this, and I won't be mean and try to force you guys to speak. So just intuitively, by the way the question is worded, if you sell an option for more than 25 cents more than quote unquote fair value, your average P&L, if you just intuit it, should be 25 cents, right? Whereas, you know, if we sold an option for fair value, in our case, 225 was fair value because we calculated an implied vol from that and then used that implied vol to generate our scenarios, which is basically like saying the world is actually going to what would I say? Yeah, the actual realized volatility of the underlying is going to reflect that implied volatility. So yeah, and if that's the case, as we mentioned above, then you're on average you should have a zero P&L. Now, if you sold it for more than 25 cents, if you sold it for 25 cents more than fair value, that means that you're going to sell the option for 250, but the realized volatility is still going to be based off of 225, which was 26.36% or something like that. So on average, you should make 25 cents. And one way you can see it super arithmetically is that for all your scenarios, your option price is going to start at 250 here. And so this first P&L, this first option P&L is going to be 25 cents higher in every scenario. And so if you average all that up, you're just going to get this plus 25 cents. Okay, any questions on that? All right. So this next question was sort of inspired by something that happened early in my career at work. And I was working at Allianz, I think, and I was doing this back test, and I had no idea what I was doing really, and I wasn't even sure if, like, you know, my code was working right. And so one thing that we did to check, like, is my delta hedging even working, is we said, well, what is the standard deviation of your P&Ls, i.e. the variability of your P&Ls with and without the delta hedge? And if the delta hedging doesn't actually reduce your the P&L variability, then something is amiss. And luckily it was working fine. And so in order to do this, let's say group by scenario, index equals false, total P&L dot sum. Okay, so that's the total P&Ls, and then let's calculate the, I don't want total P&L, I want option P&L. So this is just the naked option position, right? And let's calculate the standard deviation. What is going on here? As index. Oh. What does it look like that? I'm going to cheat. Default Pascal scenario. Yeah, I feel like that's what I have. Oh, maybe it. Okay, cool. It gets goofy. That's one thing that's kind of unfortunate about Pandas is it's a little bit wonky with the type of output you get. Okay, so what I did here was I said, well, what is the option P&L under each scenario? Just the naked option P&L. And then what is the standard deviation of that? And let's compare that to the total P&L, which is the option P&L plus the delta hedge P&L, total P&L. And let's put print statements around both of these bad boys. Okay, cool. So significantly lower. So delta hedging is certainly reducing risk. You have far less P&L variability delta hedging than not delta hedging, but there's still variability as we're as I keep hammering on. Okay. So let's calculate the okay, so here's what we want to do here. We want the standard deviation, and then we want the min and the max. Okay, so standard deviation of 75 cents. The mean is 0, so that's great, but a standard deviation of 75 cents. And the worst that we did over these 1,000 scenarios is we lost well over 100% of the option value. And the best we did is we gained well over 100% of the option value. So we can really be all over the place. This is far from deterministic when you're delta hedging discretely. So I guess I answered that question. Well, anyway, I'm just answering the question. So here's an interesting thing. So what happens if your realized volatility is actually different than the pricing volatility? So we know that if it's the same, if the realized volatility is the same as the implied volatility that you bought or sold the option at, well, then you're fine. At least on average, you're going to break even. But what happens when realized volatility is actually different from the pricing volatility that you bought or sold your option from? So that's what this huge chunk of code does, which is basically all the code that we have above. So I'm just going to run it. And notice right here. So we have our pricing volatility, but the path volatility is now the pricing volatility plus 5%. And so and this path volatility is what ends up down here for actually generating the paths. All right, great. So let's just check. That mean. Okay, so directionally, this actually makes sense. So when you sell an option and delta hedge it, you are short realized volatility. And when you delta hedge when you buy an option and delta hedge it, you are long realized volatility. So in the situation where realized volatility is higher than implied volatility and you're short the option and you're delta hedging, you would expect to lose money on average, which is what we see here. Okay, so this code challenge, I don't know why I left it as a code challenge, but I just want to actually demonstrate this, and I don't ever remember what the code is. So, okay. So let's look at a couple things here. So the question is, all right, we're losing money. Does the amount of money we're losing, does that make sense? And there's an easy way to check that. So if you recall, we have this Vega function. And if we run it for our particular option, which we're effectively doing here, we see the Vega is 0.168. So the way to interpret that is, for every 1% that volatility increases, the option should gain 16 cents in value. Another way of saying it is if you're, no, yeah, I think that's the best way of saying it, but it's also true that if you buy an option, if you sell an option at a certain price and the realized volatility, and you delta hedge frequently, that the P&L on it will be your day one Vega multiplied by the difference between realized and implied. So in this situation, so this gives you the Vega gives you the Vega position, the Vega of the position for a long position, but we're actually short, so we will want to use a negative sign, and our implied minus realized was actually, well, I guess, yeah, our implied minus realized was, I think this should say realized minus implied. Anyway, there's some negative signs. It all works out. I apologize. That was probably really confusing. But anyway, so our Vega, let me just try to restate it another way. The Vega of our position would have suggested an 84-cent loss, because right, the Vega was 0.168, and that's a per percentage difference between implied volatility and realized volatility. And if we actually run a bunch of scenarios and then calculate average P&Ls, we see it's the same, 84 cents. I apologize if that was confusing. Are there any questions on any of that? Okay, so let's, it's a lot of copy and pasting code. Okay, so here's what we want to do is, like, let's copy and paste the code above and see what happens to the dispersion of the distribution of the delta hedge P&Ls when you double and quadruple the hedge frequency. Yeah, so why don't you guys work on that? I'll give you guys a couple minutes to do that. All right, let's go ahead and talk about this. And I'm going to cheat and just grab the answers from here because I don't want to. But this is basically all the code. And that's the way I kind of structured this, this tutorial is there were lots of chunks of code. And at first, I would kind of break them up and talk about them individually, but then progressively just started putting them all in. Oh, geez. Into single code blocks. Okay, so recall here that, well, let's just run it for daily. So the hedge frequency is the thing that so yeah, as we saw from above, a standard deviation of 0.76, and it ranged from losing 290 to gaining 250. All right, so if we, so let's actually, okay, so that's for daily delta hedging. And then if we go every half day, so we would hedge twice as frequently. Oh, what happened? I went up to the wrong one. Hedging twice as frequently. So let's run that again. Okay, cool. So what we would expect, right? So if in the limit of continuous delta hedging, this thing is deterministic, we would suspect that as we increase the frequency of our delta hedging, the standard deviation of our P&L should go down, and then the magnitude of the biggest losers and biggest winners should go down as well, which we do see. And let's go ahead and quadruple just to see the pattern. Okay. And that's for quadruple. And you see everything's going down as you would expect. Although I will say that this convergence is actually slower than I would suspect. I mean, you still have pretty big dispersion of P&Ls, even after hedging every quarter of a day, which would be like every 2 hours or something in the real world. Okay, any questions on that? All right, cool. So this,
real quick.
yeah, Brady, what's up?
So if in the real world, you're sitting on the desk and wanting to delta hedge, would you actually go out and make trades yourself, or automate something to figure out what your delta neutral is?
So to figure out what your delta neutral is, you would probably have a position management system doing it. When I worked at Cargill Risk Management, we would just hedge our deltas by hand. At Wolverine Trading, which is an option market maker, they have thousands of hedge positions or option positions. So they basically, everything is automated. Does that answer your question?
Yeah, cool.
Yep.
Thanks.
All right, guys, it is 7:35, so let's go ahead and get back into it. Okay, so we are done with this tutorial. Jump into Jupyter Lab. I'm going to go to my desktop, linear regression. Cool, and I'll give you guys a moment to get caught up. Okay, cool. So this tutorial is really just an intuitive introduction to simple linear regression. We're going to use a finance example since this is a finance program. And really the goal here is to just learn, also to learn about sklearn, which is a package that is used for a variety of machine learning techniques. And it's super useful, and it's going to be sort of the primary tool that we use for our various machine learning tasks. So we are going to fit a couple of different regressions that demonstrate a couple of different stylized facts about volatility, index volatility. So one is called the leverage effect. Oh, and I should add, we're going to be focused on SPY, which is an ETF that tracks the S&P 500. So all our data is going to be related to SPY. So again, we're trying to demonstrate two stylized facts. The first is called the leverage effect, and that is that there is an inverse relationship between implied volatility and returns. So what that means is basically when the market goes down, implied volatilities go up. When the market goes up, implied volatility goes down. And the second thing that we stylized fact is called volatility clustering. And that means that if you have high volatility now, that's going to lead to higher volatility in the future. If you have low volatility now, that's going to lead to low volatility in the future. So that's volatility clustering. Volatility clusters in groups. It's high in certain periods, and then it's low in certain periods. And really, we're going to eschew the mathematical and statistical details. We'll touch on that a little bit next week when we go over some slides. I wanted to just focus really on tutorials this time around. So, okay, so let's go ahead and import the packages that we are going to need. Oh, let me confirm that I am recording. Yep. Okay. Matplotlib. I don't think I actually need this anymore, but I'll just type it out. Inline. You used to need to do that in order for plots to actually show up. So we're going to import matplotlib.pyplot as PLT. Import Seaborn as SNS set. Import Pandas as PD, and import NumPy as NP. And finally, we're going to import scikit-learn, sklearn. Great. So now we're going to load up the data set that we're going to need, and it's going to consist of a variety of weekly volatility metrics for SPY during the time period of 2014 through 2018. So each row of the data frame that we import is going to be a set of observations from a specific week. So let's go ahead and just read this in and then talk about what we've got here. SPY, df_SPY equals pd.read CSV. SPY. DF SPY head. Okay, so we have realized volatility, which is the realized volatility during this week. We have the return, which is the weekly return during this week. And we have the starting implied volatility, which is the it's technically the variance swap rate. Don't worry about what that is. Just think about it as at the money ball or some kind of aggregate volatility measure. Okay. So options are simple insurance contracts that are written on top of an underlying stock, right? So really what they protect against is large moves in the price of the underlying stock. So puts protect against large downward moves, while calls protect against upward moves. So the implied volatility of a stock is a measure of how much the market is willing to pay for options, for insurance on that stock. So the implied volatility could serve as an index of how fearful market participants are about large moves in the stock price. So again, the leverage effect means that for many stocks, especially index linked ETFs, the following two relationships hold. So if implied volatility increases when the stock experiences losses, and implied volatility decreases when the stock experiences gains. And that sort of makes sense. When the market goes down, people start getting freaked out that the market's going to go down more. When the market goes up, people are less concerned about the market going down. So let's see if we can just visualize this relationship with a simple scatter plot. So the first thing we need to do is we need to add a column to this data frame that tracks the changes between these start IVs. So DF SPY, we're going to call it IV change, equals DF SPY start IV minus DF SPY start IV shift 1 shift -1 DF SPY. Okay, right. So from January 3rd to January 10th, IV went down 1%. From January 10th to January 17th, implied volatility increased by about 1%, et cetera, et cetera. So now we're going to use Pandas built-in plotting functionality to see if we can visualize this. Plot, scatter, return, IV change. We're going to make the color black. And we're just going to cool. So this is what we would expect. We've got a clear sort of negative relationship. We've got returns down here, IV changes here. When returns are negative, implied volatility increases. When returns are positive, implied volatility decreases. So if we were just doing an exploratory data analysis, then probably all we would really need to do is look at this visualization, say, yep, there's clearly a negative relationship. But if we want to make this more precise, we could do so by fitting a linear regression line to the data. So linear regression is a simple model. It's one of the simplest sort of machine learning techniques that purports that implied volatility change is a linear function of the return. So intuitively, when we're fitting a linear regression, we're trying to find the straight line that has the minimum aggregate distance from all these points. It best fits these points. So language is slightly different between statistics and machine learning. So in statistics, the return is called the independent variable, and the IV change would be called the dependent variable. In machine learning, we use slightly different terminology. The return is called the feature, and the IV change is called the label. So in a generic supervised machine learning problem, we are seeking to predict a label from one or more features. So we'll use that language frequently. So we're going to use Sklearn to fit a linear regression to our data. And the cool thing about Sklearn is that it's got a very sort of simple and consistent interface with which you use to fit, I'm sorry, and work with all the different machine learning techniques. And so once you learn sort of the basic sequence of steps for one machine learning technique, it's very simple to apply that to different machine learning techniques. So the first step in any sort of machine learning technique with sklearn is to instantiate the model object with a constructor function. So our constructor function is called linear regression, and it lives inside this linear models submodule. And we're going to call this model, we're going to put it in a variable called IV model. So from sklearn linear model import linear regression. So we're going to import the constructor function from sklearn. IV model equals linear regression fit intercept equals false. So, and what this fit intercept equals false does is it just says we're going to force the line to go through the origin, which is looks fairly reasonable just by visual inspection. It looks like this thing does really go through the origin. Okay, so the next thing we want to do is kind of separate out the data that we're going to be using to fit the model. We want to put the features in a data frame, and we want to put the labels in a data frame. So our features are the returns. So we're going to grab those, df spy. And changes in IV are our labels that we're trying to predict. Cool. Well, I suppose I should just stop and see if there are any questions thus far. Excuse me. Okay, so now we're at a point, since we've got our features and our labels separated out, we can go ahead and fit our model, which is done with the appropriately named fit method of our model object. IV model fit df return df IV. IV. Oh, whoops, I didn't actually run this, sorry. Cool. So now that's done, let's check our intercept and coefficient. Okay, so what this says is that that IV change and weekly returns have this linear relationship. So what does that mean? So for every 1% of positive weekly price return, this leads to a drop of implied volatility of about 2.175%. And in sklearn, once we have a model fit, we can use the predict method of our fitted model to predict labels for a given set of features, right? So in our example, we can predict implied volatility for a given set of weekly returns. So let's try this for a few different values of weekly returns. So our test values are going to be 5%. Oh, I'm sorry, negative 5%. 0 and 1%. We have to use this reshape to get the array in the correct format. Yeah, and there are a lot of these array gymnastics that I don't even remember, and I always have to kind of Google them to figure them out. Cool. So for these levels of weekly returns, what would be, these are the changes in implied volatility that would be predicted. And it's simple. We could have just read it off using this, but I just wanted to demonstrate that there is this predict method. And so when you have models that are more esoteric or just can't be defined easily with an equation, you will use the predict function to actually create predictions. So another thing we like to do is in these types of situations, actually see the line that, that gets fitted, and we can use the predict method to kind of like hack a solution for ourselves. So let's just first create the range of the line, the range of the possible weekly returns. So we're going to have a line running from -8% to +5.5%. We're going to use a predict method to come up with predicted values for all of this, for all of those values. XFIT. And then let's actually create a scatter plot with all this. TFSPY dot plot scatter return IV change C equals K black big size. Okay, so that's the line that gets fitted through our data. Any questions thus far? This is probably pretty straightforward for you guys. Okay, so in sklearn, all models, all machine learning models also have a score method associated with them, which gives some kind of sense for how well the model is performing. And so for linear regression, the score gives a R squared. R squared can be interpreted as the percent of the variance in the label that's explained by the features. So let's go ahead and take a look at that. IV model, score, DF return, DF IV. Oh. Sure, so what that says is that this regression explains 59% of the variance in weekly implied volatility changes from weekly returns. So is this good? Like, is this a good R squared? So really there is no universal notion of what is a good or bad R squared. It's really context dependent. If you're doing regression in, I don't know, a particle physics context, you would probably expect, you know, R squareds very, very close to 100 or 1. I would say in finance, an R squared of 0.59 is pretty strong. And if you're, let's say, in psychology or some other social science, an R squared of 25% or might be good or might be considered strong. So it really does depend on context. One thing I do, one kind of dose, I guess, dose of reality I want to put in here is that this isn't really a predictive model in the sense that these two occurrences are happening simultaneously, right? It's not like returns, and we'll see in the realized volatility clustering, more of a true predictive type of model where the R squared is a lot lower. So it looks like the relationship's really strong, but sort of we're sort of observing things that are happening simultaneously. Any questions on any of that? Okay, so again, let's move on to volatility clustering. So again, I mentioned this, there's this stylized fact about financial asset returns that realized volatility tends to exhibit clustering. So high volatility tends to be followed by high volatility, and low volatility tends to be followed by low volatility. So we want to first kind of observe volatility clustering in our SPY data and then analyze it more specifically with linear regression. So the first thing we want to do is kind of observe the relationship between the current week realized volatility and the subsequent week realized volatility. So we're going to create a couple new columns in DFSpy. Let's just take a look again what DFSpy looks like. So, right. So let's create a column called real vol 0. Realized vol. And DFSpy. Shift -1. Okay, cool. So here we've just really this is just a copy of realized volatility, and this is shifted up 1. So this is current week realized volatility, and this is the realized volatility for next week. So we're going to ultimately see how this predicts this. So let's take a look at the scatter plot here. Real vol 0. Real vol 1. The color is black. Oh. Okay, so there are some positive things going on, but there's also some problems. So the relationship is clearly positive. You know, that's good, which is what volatility clustering would say. Current realized volatility high current realized volatility leads to higher subsequent realized volatility. But this isn't particularly suited to linear regression. First of all, things are really clustered around 0 because returns are usually close to 0. And additionally, standard deviations are all positive, right? And so, so this doesn't look very linear in nature. So for both of these reasons, we're going to take the logs of both of the variables to make the sort of linear relationship more apparent. Meaning there's a more of a linear relationship between the logs of these values than the raw values themselves. So let's just repopulate the columns with the logs values that we really want. DFSpy real vol 0 equals NP log DFSpy realized vol equals NP log TF spy head. Oh, sorry. Okay, cool. So there's the log realized vol values. And now let's look at the scatter plot. And we're going to again set our fig size to 6. Okay, so now that's looking a little bit more linear-ish. So again, we're going to proceed as we did before. We're going to instantiate a linear regression model with the linear regression constructor. We're going to isolate our features and our labels for fitting. Then we're going to fit the model with the fit method. And then we're going to check for goodness of fit with score. All right, so let's call it RV model. And let's put in a linear regression. Fit intercept equals true. So we are going to fit the intercept this time. Okay, next let's grab our features and our labels. So these are our features. It's current volatility. GFRV1 is our label that we are trying to predict. So future volatility. What's going on here?
I think you got some commas in there that you don't need.
Oh yeah, that's right. Sorry. Thanks, man. Anyway, so now we've got our features and our labels. Let's go ahead and fit our model. And let's just eyeball our goodness of fit with by plotting our line. We're going to go from negative 4.5 to negative 0.75, 100, Y fit, RV, model. Oh. P, new axis. Create a scatter plot of real vol 0 against real vol 1. And let's go ahead and plot that. Cool. So there's our fitted line. And we can, of course, check the R squared with the score. method, the score method. So since this is an actual sort of predictive situation where we're looking at something currently and seeing how well it predicts it in the future, there's a more modest R squared. Okay, any questions on that? Okay, so so far when we run our regressions, we use the entirety of our 5 years of SPY data that we have available. So this is typical in a situation if you're just using your regression for exploratory data analysis, or simply to confirm some kind of directional relationship between the two variables. But oftentimes in machine learning, we want to do more than just exploration. Our ultimate goal is prediction or forecasting. And if you're serious about that objective, it's appropriate to split your data into a training set and a testing set. And these separate sets are used for two distinct purposes. So with the training set, you actually train and fit the model, and that's called the training phase of the process. And then you use the other set of data, the testing set that you held out, and feed those values into the trained model to produce predictions and analyze how well those predictions actually fared against reality. So this is called the generalization phase or the testing phase. And we'll explore this more with train test split and cross-validation when we talk about other machine learning techniques. So let's try this let's try this two-staged approach ourselves. So so rather than fitting a linear regression to the entirety of our data set, we're instead going to only fit it to the first 4 years of data, 2014 through 2017. And then we're going to use that fitted model to forecast realized volatility throughout 2018. So let's call this model the forecast model, FCST model. Linear regression fit intercept equals true. Let's grab our training data. So we'll call it df rv0 train equals df spy real vol 0. I didn't want to bother with any kind of filtering, so I just eyeballed where the values were for the first 4 years of data. RV01 train. So these are our labels. df spy real vol 1. Great. Now let's go ahead and fit our model. df rv1 train. Cool. And I'm not going to have us type all this out. So let's print the coefficient, the intercepts, and the R squared of the model. Cool. So here's our coefficient. Here's our intercept. And the training R squared is 0.21. That's all summarized. Here's the linear equation. the resulting linear equation. So now we're going to take this model and we're going to apply it to our data from 2018. So let's go ahead and separate out our testing data. So it's 2009 and beyond. So there are our features. Okay, cool. And now we can go ahead and we can check the score if we, we plug those into our model. All right. So one thing to notice here is that our R squared from our testing set was lower than the R squared from our training set. And that's always going to be the case for all models. However good your model seems to be working on the training data, it's going to work less well on data from the wild or testing data. And that, I mean, the intuition is clear. So sort of when you're trading a model to data, you are optimizing the model to that data in some sense. And so when you take data from outside of the training data, you're going to have worse performance. So another thing I want to point out here is that there is this Sklearn metrics module where you can have a variety of, you can pull a variety of other goodness of fit metrics. And we'll explore some of those later, especially when we do our student loan default exercise. So R squared lives in that module as well, and we could use it directly with this code. So Sklearn metrics R2 score df rv1 test against the forecast model predictions. If you stuck in df rv0 test, you get the same result. All right, very good. So, okay, so in the forecasting exercise above, in our linear regression, our model was trained from data from 2014 through 2017, and then we used that exact model, and that one model and all of our 2018 forecasts were based on that model. So that's probably not what we do in practice. Instead, we would update our model on a regular basis and make predictions based on that new model. So the following code basically walks us through that, and we don't have to type all this out, and we don't even have to go through it with a fine-tooth comb. But basically what's happening is every week, you're actually using the four years previous to fit a model, and then you're using that model to make your next prediction. So you're constantly updating your model. So, and let's just take a look at how doing that performs. What are we doing here? Oh, here we go. Miss parentheses. Okay, cool. So one thing to note here is we had slightly better performance by updating our model every week rather than just fitting it once through 2014 through 2017 and then doing all our predictions based on that. Cool. So here's some further reading. Oh, and this is the Python Data Science Handbook. I think I actually linked to this in the syllabus. Yeah, it's a good little, it's an interesting little book. It's all available online. I definitely learned some things from it. So anyway, go ahead and follow the links. Let's go ahead and crack in on the next tutorial. So this is tutorial 3, testing the CAPM. Okay, so this tutorial was inspired by a couple of things. One, this paper that I was reading. Cool, so it was written by Fama French, and it's kind of just an overview of various ways that people have tried to do statistical analysis to either verify or invalidate the capital asset pricing model. And so I thought it would be cool to, I was actually also, I was doing this, I was leading this group of students in the Master's of Science in Finance program at the Carlson School of Business on a project on some REITs that we were doing for a local hedge fund. And so I had a bunch of REIT data, and I thought, hey, maybe a lot of times these analyses are done in the context of stocks. And could I try to reproduce some of the results with the REIT data that I had? And so this is a graph that I'm basically going to try to reproduce. And a spoiler alert is that when I run it on the REIT data that I have, it doesn't look anything like this. But I'll kind of explain what this graph is as we work through the slides. I'm sorry, work through the tutorial. So cool. So there are various versions of the CAPM. The Sharp-Littner version says that the expected return on an asset is equal to the risk-free rate plus the difference between the market return and the risk-free rate, which is sometimes referred to as the beta premium, multiplied by the beta of the stock of the asset. And the beta of the asset is defined as this: the covariance of the two divided by the variance of the market. So when we talk about testing the CAPM, we mean testing one of 3 of its implications. The first is that expected returns are linearly related to their betas, and this beta is the same sort of interpretation as the coefficient in a simple linear regression, right? So basically that expected returns are defined by this very simple linear regression model. So expected returns of assets are linear related to their betas, and no other variable has marginal explanatory power. So that's one of the implications. That the beta premium is positive, meaning that expected returns on the market portfolio exceeds the returns on the risk-free rate. And that's actually, there's a homework assignment associated with this tutorial, and that's the portion of it that, that you guys are going to be testing for. And which is really just an exercise in data analysis and some of this group by gymnastics that we end up doing in this tutorial. And that the beta premium is the expected market return minus the risk-free rate. Okay, cool. So performing tests on the CAPM for individual securities can be problematic because when you try to estimate betas for individual securities, those estimates can be very, very noisy. So in order to address this noisiness, we're going to perform the test on beta sorted portfolios. And I'll explain what that means in a second. But it's valid to test CAPM to portfolios of securities because it applies to individual securities in the same way that it applies to portfolios of securities. So, and we're going to organize our universe of securities into beta rank portfolios because that's going to give us the widest range of betas to work with. For example, if we just randomly generated portfolios, then the range of realized betas that we would see in our analysis would be compressed because you'd have high beta stocks combined with low beta stocks and or REITs in our example, or in our case, and it would just all those betas would sort of average out. So here's the data that we're going to have, and here's the test that we're going to actually perform. And along the way, we're going to describe what it means to have beta sorted portfolios and construct beta sorted portfolios. So really what we're going to perform a test on the time series version of the CAPM. I think this should say Jensen 68. Anyway, I'm not going to bother with it. Which looks like this. It's a very similar form, but it's just stated slightly differently in terms of time periods. So the data that I have is price and market cap data for 100 REITs from 1999 to 2019. And our test proceeds as follows. So basically each December, we're going to use the 2 years, the 2 previous years of monthly returns, and we estimate a beta from those. We'll calculate sort of the trailing 2-year beta for monthly returns, and we'll call that the pre-ranking beta. And we're going to calculate the beta against the market portfolio, right? And we're going to define the market portfolio to be the cap-weighted portfolio of all 100 REITs. So once we have these pre-ranking betas, so we're going to have some betas that are high, some betas that are low, and we're going to rank, we're going to just order up all the betas, and we're going to form 10 market cap weighted portfolios based on the deciles of these pre-ranking betas. So what does that mean? It means we're going to take the top 10 betas, or the REITs with the top 10 highest betas, put them in a portfolio, then the next 10 highest betas, put them in another portfolio, and so on and so forth. But we're going to change the composition of these beta rank portfolios each year. So at any given time, there is a such thing as a top decile beta rank portfolio, but the constituents of that portfolio are going to change once a year based on this 24-month trailing beta exercise that we do. So yeah, so then we're going to calculate monthly returns for each of the beta rank portfolios for the next 12 months. So, and we're going to repeat this process every year from 2001 to 2019, which is going to result in 228 monthly returns for each of the beta rank portfolios. And so then we'll be able to, for each of the beta rank portfolios, we can calculate its average annualized return from 2001 to 2019, and also its realized beta over that same time period for the beta rank portfolios. So, and then we're going to plot these to test for a positive relationship between realized beta and realized return. So again, that's what this looks like. So you have all these points represent different beta ranked portfolios. And here's the actual beta that they realized over this time period of 1928 to 2003. And here's the actual average annualized return. So this one realized like a call it 11% return. This one was also around 11%. But the constituents of these portfolios is changing every year. Any questions on the construction of the beta rank portfolios and how we're going to proceed? Okay, so and this there's a lot of just like messy blocks of code in this, so I'm not even going to bother typing this out. We'll just sort of talk through what's happening. But I will actually just restart kernel, clear all outputs. Cool. I will actually run each individual. Okay, so first of all, we're going to import the packages that we need. Next, let's read in the universe of names that we'll use to form this backtest. Okay. So here's all the various reads. We don't actually end up using, you know, the type of read or the sector. So let's go ahead and read in our price data. So here we have open, high, low, close, volume, and adjusted for each of our tickers and each of the days. And there's actually a lot more data in DF price all than we need. So all this code does is isolate the data that we want. So there's filters in here. Another thing that I do, and all we need is the close price and the adjusted price, so that's all I grab. And another thing that I do is I pull out the year and the month from the date, because we're going to ultimately group by months, because it's a monthly sort of analysis. Okay, so let's go ahead and calculate the monthly returns for each of the REITs. So this is actually going to be easiest to do by first calculating daily returns and then calculating monthly returns from that with a group by. So we'll go ahead and just calculate the monthly returns. There's this percent change convenience function. So when I pair that with a group by over symbol, it does exactly what I want. And we're using the adjusted price here. You should always use the adjusted price when you're calculating returns over a long period of time, because dividends are an important part of long-term performance. If you're calculating like volatility or standard variances or volatility, less of an issue. And especially in the case of REITs, they do pay out dividends, large dividends relative to their stock price. And so it's an extremely important part of their performance. Okay, cool. So in order to calculate multi-day returns from a single day return, we're going to use this user-defined function, which takes in an array of returns and produces a multi-day return. So we'll use this cumulative return function to now calculate all the monthly returns that we need. Cool. So here's the monthly return for January 1999 for ADC, et cetera, et cetera. Cool. Okay. So now let's calculate the monthly returns for the cap-weighted market portfolio. And just to note, for any given month, we're going to use the market cap from the last day of the previous month. So for January 1999, we're going to use market cap from the last business day of December 1998, which was 12th Christmas Eve, or I'm sorry, New Year's Eve, 1998. So let's go ahead and read in our market cap information. And then this code calculates the total market cap for the entire REIT universe. So, and then this following block of code here calculates the monthly returns of the cap weighted market portfolio. And so, and if you're, it's kind of burly, and if you're curious as to what's going on, you can definitely run it line by line. I remember when I was reviewing this and editing this, I did that myself, just because a lot of times when I write a block of code like this, I can only retain it for a little while, and then when I come back to it a year later, it's definitely foggy. Okay, but here are the market returns for the cap weighted market portfolio, the monthly returns. All right, any questions so far? So let's now actually go ahead and construct the beta ranked portfolios. So in order to calculate the pre-ranking betas, we're going to begin by calculating a rolling 24-month correlation between the securities and the market portfolio. And actually, we're calculating a bunch more correlations than we need because it makes the coding easier. So we'll go ahead and calculate rolling 24-month for every month, and then we'll just we'll filter out what we need. So here are the rolling correlations. Here are the 24-month rolling volatilities. And we're going to calculate a bunch of betas that we don't need, but some that we do, because it makes everything easier. So now what we're going to do is we're going to give each REIT beta ranking for month one, right? So now we've actually calculated betas for every month, rolling 24-month betas for every month, but we really just need it for basically January or the end of December, and for the year 2000 moving forward, or 2001 moving forward. So what this data frame says is that for January 2001, ADC had the 36th lowest beta. And for January 2002, it had the 15th lowest beta. Cool. So I always like to sort of visualize real quick whether the code seems to be working or not. And so if I sort by year and beta, we probably want year, month. Doesn't matter. I think it seemed to work fine. Cool, yeah. So, yeah, as you can see, beta of negative 1.4 was the lowest. So these are going in the correct order. So everything's working just fine. So now, in order to group the REITs into deciles, we're going to use this custom function called rank group. And then we can just use the apply method to actually apply that to the various. So what this says is for ADC for year month 1. Oh, it doesn't actually. Sorry, I'm talking to myself. So for 2001, ADC was in the beta portfolio 4, but for 2002 it was in beta portfolio 2, et cetera, et cetera. So an individual REIT will move around in terms of what beta ranked portfolio it is in for any given year. So again, let's just do a quick little sorting. And we can see that, yes, so all the lowest ranked betas are in beta portfolio 1. Just a quick little visual test that everything's working. So let's go ahead and now calculate the total market cap of the beta ranked portfolios at the beginning of the year, because we want the, these are going to be cap weighted portfolios. So those are the total market caps. And now we can calculate the weights of each of the portfolios, of each of the REITs within the within their beta rank portfolio. Okay, cool. So that now gives us the construction of the beta rank portfolios. So what are we doing here? So now it's a matter of calculating. So now that we have our sort of portfolios organized, it's really just a matter of calculating their realized betas over 2001 through 2019 and their realized returns. So let's go ahead and. So here are the realized correlations for each of the beta rank portfolios. These are the realized volatilities for the portfolios and for the market. And that leads to being able to calculate the realized betas. And finally, we can calculate the realized returns. Okay, so I'm trying to hurry along here just because we have just a few minutes left. So we're gonna merge everything together and then take a look. So obviously this graph looks really, there looks to be a downward relationship between realized beta and the portfolio return. So I guess since we're running low on time, I'll just kind of explain what I think might be at the heart of some of this stuff. The discrepancy between my graph and their graph. So one thing is that the time period, they used a much longer time period than I did. I had 20 years worth of data and they have like 75 years worth of data. So that could be one thing. And I think another thing is that they probably use like a universe of 5,000 stocks, whereas I had only data for 100 different REITs. And so there might just be it just might be not enough data to really like work out the noise. It's a small time period and it's a small data set. And also the CAPM return refers to, or the CAPM refers to the entire market. And obviously, and so a lot of times when you're doing a stock analysis, you know, they're just using this giant universe of stocks as the market, but really technically the market includes all investable assets. And so not only are we not including all investable assets, but we're only including 100 REITs. And so it could very well be the case that, that just doesn't really hold up.